Hello, we start with this seminar. So good afternoon to everybody in Europe, good evening to Asia, and good morning to the United States. I am Ulrich Kissling, and I would like to give you an introduction today in the layout process of a gear set step by step as we have it implemented in KISSsoft. We have three main stages. Stage 1, Stage 2 and Stage 3. And okay, Stage 1 is defining raw dimensions, which is the relatively old. We have a short problem with the acoustic. Okay, row sizing is stage 1, stage where we principally get in with requested speed, torque, power, and as answer we get out the overall dimension of a gear set, center distance, and phase width mainly. Then stage 2 is the macrogeometry definition. Macrogeometry is module, tooth number, pressure angle, helix angle, and so on. This is our so-called fine sizing. And then we have microgeometry sizing, which is relatively new, where we can, in 3 steps, where we can define flank line modification and profile modification. So I will directly start in KISSsoft. Okay. And call the cylindrical gear pair, and this is the setup which is now loaded, and to do the row sizing, which is this button here, I have just to add certain power. I will put here 75 power for a 75 power kilowatt motor, and maybe a speed of 980 RPMs on the input side of this gear set. Basically, that's all which is needed. Clearly, all the rest of the data, as for example the material choice here, is communicated then to the fine sizing using the fine sizing, reference profile, and the setting of the factors. So if I start the row sizing, the main thing you have to introduce is the ratio. Maybe we say, okay, we want a 4.25 ratio with an accuracy of maybe 3%. That's normally your customer, which is telling you, I would like to have a gearbox from you for this power with this ratio, and maybe he will tell you I need to fit this gearbox into reduced space, so the overall dimension of the gearbox can be critical, and this is one of the topics we will find out here. The input for the helix angle is not very important. Means we ask just here, do you plan to have then a spare gear set, or should be a helical gear set? If it would be helical, we just could put 15 or 20 degree. Doesn't matter so much. Important is that if we have helix angle, we have higher, or we have some axial loads, means we have to be careful when we then select the bearings. What is important to explain are these factors here. I think you know some books about gear design, and in all these books for a gear set you will see maybe the book from Niemann from Munich University says that for industrial gearbox the ratio of phase width B divided by module is should somehow be between 6 and 20. 20 is the maximum. If it's larger than 20, you will have a relatively always worse load distribution over the phase width. If it's too small, this ratio, then your gear will be very, very narrow and maybe have a flexure or something like that. So that makes not much sense. If it would be to design automotive a shifting gearbox, there things are completely different. You know, in automotive gearbox you have 5 shifts, 6 shifts on the same shaft, so the gears must be very narrow. There I would put maybe 4 to 6 and not 6 to 20. But we will go on now. These settings are for industrial gearboxes. So if I click on calculate, the process is very fast. I try to increase the window. Okay, you see the numbers here are completely out of order. This was because before I changed the order to some other feature here. I will explain you that. Now I clicked on numbers and I'm back on the alphabet numerical order. We have in this list, if you look to the module, we have normally the first 5 variants have a somehow very special module, and the other ones from 6 on, they are all standardized modules. There is a DIN standard giving standardized modules, which is here activated, and so you get only rounded modules 4.5, 5.5 and so on. The first ones are exactly giving you special information. Number 2 and 3 gives you the biggest here, number 2, and the smallest center distance. The biggest and small, the range of center distance possible for this gear set. If your customer comes and says, I want to have a center distance of 100 millimeters, you see at once this is excluded with the material we have chosen, which is already a very good material. So basically you can say with the safety factors which are used for this layout, which were here under module specific sizing, required safeties, you see we have always a module bigger than 2, so the dimensioning, the layout was made with a safety factor 1.4 for bending and 1.0 for pitting. Let's go back here. And the number 4 and 5 shows you the smallest possible and the biggest possible module, always for this application, just that you have an indication what would be possible. When I run this calculation, for me the most important result is, or I have a request on the maximum minimum dimensions, or if not, I go on the right side and I have a look on the white. I click here in numerical order of the white, and you see the lightest variant has a weight of 30 kilos and the heaviest 51. So we have a big gap here. And if you think that, or if you remember that the white is relatively near to the manufacturing cost. Very often used if you do a simple calculation of manufacturing cost, you just use the white. So this is a very good indication. I put it here in numerical order according to white, and then I go back here and I see, oh, the best white is here around 200 center distance with a corresponding phase width. So if the first solution with model 3 24Ts, you like it, we can take this. I like, in my opinion, I would prefer to take a lower tooth number, maybe model 4, this one, and if I do a double click on the solution, I can still let open the window and I get automatically back this solution. I can have a look at the already calculated, I can have a look at the meshing, I can have a look at all the other results. You see, here we were very near to 1 for safety. The root safety has a little bit more reserves compared to 1.4 requested, but here the opinion with pitting safety of 1 is the limiting thing in this configuration. Scaffing is high, so I think can be a good solution, and we can use this and then go on in the fine sizing. We can also say, 196 is not so a nice number. I would prefer a round one number, maybe 200, and maybe here phase width 48, 46 to have round numbers. This is clearly optional. I can redo the calculation and you will see little changes here, and the safety factors clearly here are not anymore so good, and you see the profile shifts are now a little bit inverted, should be improved. Now we will get already again better results, but this is absolutely optional. The main idea is that in the second step we go to the fine sizing, and there we improve the macro geometry. This was just to get an idea about center distance and phase width, which would give us a well-dimensioned gear set. Let me go back here a second. So we go then to stage 2. This was stage 1, I already explained you. Now stage 2. Stage 2 is a very, very important stage. Stage 1 is optional. If you start at 0, it's nice. Stage 2 is very often, in many situations, you should use just this layout process, because the basic idea here is we have as input the center distance given and the phase width given. So you can use this stage 2 process often also if you have to improve an existing gearbox. We have a gearbox which fails for pitting, maybe for bending, maybe for other things, maybe it should be less noisy, and for all these aims this stage 2 is very powerful, because basically in an existing gearbox what you cannot change is the center distance. You would have to completely do your housing, and normally the phase width you can change maybe a little bit, but not too much. So this is what is basically what is given. If I go back here, now I will close the row sizing, and I will call directly with the data I have here which is constant. I calculated it, and I go now to the fine sizing. Fine sizing has a similar user interface as before, but here you see the solution I take over from the row sizing was not 2.45, 2.25, 4.25, sorry. So I put back that I request a 2.45. What was shown here was the exactly ratio of the solution I took over. So I put it back to 2.5, 4.5, sorry. Now, what I can change in an existing gearbox without changing the center distance and without changing the faces here is the module. I can say I would like to have module from 3 to, let's say, 5.5, step of, let's say, 0.25 or 0.5, whatever you like. Then we can change the pressure angle. As long as I change the module with mathematical nice steps, I can be quite sure that I will find tools, corresponding tools in the machining department. If I change the pressure angle, that will be hard. Means if I change the pressure angle from 15 degree to 25 with a step of 2.5 degree, it may be hard to find the corresponding existing tool, so you risk that you have to buy a new tool if then you will produce the solution. For the helix angle, we can say we change now to helix angle, maybe from 10 degree up to 25. Let's do also a relatively big step, otherwise we get too many solutions. Just a step of 2.5 degrees. Helix angle is free of charges. I mean, with every tool you can produce any helix angle you want. Okay, so these are the main things to vary, which will produce us a lot of solutions. All the software will find you all the solutions which are fitting into this condition 200 center distance. The rest of the input is very optional. You may need to fit a new reduction into an existing gearbox. That can mean that your tip diameter of the variant has to be smaller than something. The gear cannot crash with the wall of the housing, so that can be a restriction which you should input here. Okay, I just let it run. Now you see it takes a little bit of time to run through. We have the maximal number of solutions reached. So the meaning is here, I told the software, do not do more than 1,000 solutions because of time. And we have now, the software stopped now at a module of 5.5. So we are very near to the end. So let's do the following. I increase to 2,000 and I repeat the calculation, because I will not risk that because the software stopped at 1,000 solutions, that I do not see some of these. Maybe the last 62 solutions are good to see. So now we have them. Now we have all possible solutions up to 1,060. I didn't show you condition 2. Here you can additionally change the reference profile. Be careful with that. If you change the reference profile, it is a nice feature, but you will need clearly a special tool to produce then as a solution. Conditions 3. has other things, a lot of different things here. The most important are that you can say what we activated here. Don't kick out or eliminate automatically solutions which have a too high specific sliding. You know, specific sliding over 3 is not a nice solution, maybe too much sliding. Then normally we would like to have the tooth thickness as needed, also a good thing to consider it. That means if the tooth thickness is too small, the variant will not show up in these 1060 solutions here. We have these things here mainly for special cases, for example, power tool. In power tools, hand bore machines, for example, you have very often spare gear with pinion of 4 teeth, and if you would like to have a solution in that range, you always get undercut and other nice things, so you have to admit such solutions. Then you pick out what you look like a nice solution. You have to refine it then later in the basic data. Other thing is, very nice thing is here, sorry, not this, deep tooth form means you could tell the software here, I want all solutions with overlap ratio of 2 or 2.1. These are so-called high tooth profile or deep tooth form profiles for producing low nose solution. Very good technique, very fast, perfect thing. You will find a lot of solutions, not as many as I found now with a normal reference profile, but this is a very good topic. Okay, if I have a look at the results, you see many results, very hard to find out what you want. You know, in KISSsoft you can click on the right mouse button and then show hide columns. You see here all the results which could be visualized. The one here with the flag are visualized, and you can customize this as you want. I'm, for example, interested in the overlap ratios, epsilon alpha, epsilon beta, the total overlap ratio, and so on. But clearly, you can export this table through save into an Excel sheet in Excel format and then do additional things. But the most important thing is here to open the graphics. Now the graphics looks quite nice. It's like a cloud. We have many users who are doing that. They will have a look where are the best range of solutions, and then they redo a run with, for example, starting at the higher module, not from 3 up and so on. Sorry, I don't see. Nice. So, okay, here. You see here now the pressure angle is shown. I will start here with the module. You see the x-axis shows the minimum root safety. That means the lower of the safety bending for pinion and gear. And here you see the flank safety. And just to looking at that, remember, same center distance, same phase width, so basically same manufacturing costs, and we have a safety variation from about 1.2 up to 3.4. So more than 2 times more safety or torque capacity here than here. That's amazing. And similar thing applies for the flank. We are from 0.95 up to 1.2 flank safeties, and remember, flank safety is based on Hertzen pressure law, and that means if you change the safety from 1 to 1.1, maybe, so 10%, it means in torque capacity 20%. So from here to here we have more than 30% increase, and that means we have about 60% more torque capacity. Not as much more as in the bending line here, but still it's a lot. And what is very nice to see, you see the normal module is now the color here. So red is 505, blue is module 3, and you see very clearly high module gives high safety factor for bending. But in the flank area, you see from here to here, same module, but very different flank safety. So the module and the flank safety are not interconnected, or very little. If I change to pressure angle, it's different. You see over all the bending safety, about red means the pressure angle has no impact on the bending safeties, but a lot of impact on the flank safety. You will know that it's maybe trivial, but it's nice to see it here. Everybody, I think a lot of people knows that increasing the pressure angle, as you see here, will increase the flank safety, a lower engine pressure. So depending on what you want, you can find here an improved solution. And as we had consistent situation when we started the fine sizing, you see also a variant 0, which is the variant coming, which was calculated here. And this 0, I don't see it, too many solutions. It has 1.75 and 1.0 here. So 1.75 should be here and here. Somewhere here. Normally you see it, but we have so many solutions. Maybe I have to increase to see the solution 0. I don't see it, but it's, let's say, it's somewhere here. This one. You see here 0? Very hard to see. This is the solution 0. So we have all the solutions which are on this side and up from here are better than the actual solution. This is one way how you can find, if you would like to have best bending, you would take this solution. If it's more for flank and also for bending, maybe 482, you just say, okay, I would like to have 482, 482. You produce a double click and the solution is arrived here in the main calculation. One more short comment. You can here also activate contact analysis. You could for every solution do a calculation of the transmission error, but with 1000 solutions this will be very time consuming. The better idea is now look at your solutions here, kick out maybe in the result table everything you don't want, and then you can recall the contact. It's shown here. Sorry, this I don't need. Sorry. You can here say now, you can delete solutions and then say, add now the contact analysis, then for the remaining solutions, contact analysis transmission error is calculated. Okay. So I come back here with a solution from this fine sizing. I stop here with fine sizing. I hope you get a little bit the overall picture. Fine sizing for planetary is a little bit more special, even more powerful, because in planetary gear sets it's much harder to find, to improve macrogeometry. You have two pairs in contact, so it's more complicated to find directly here in this user interface good solutions. So the fine sizing for planetary is even more, is really helpful. I will now go to the modification sizing. Modification sizing is a little bit more complicated, but it's very important. I may repeat, I saw a lot of people producing a proposition for a gear stage and not thinking about the macrogeometry. They do anything hop hop and then they directly go to the microgeometry, and this is bad behavior. I mean, you have seen now in the fine sizing of the macrogeometry, you can improve already by factor of 2 what you want to get out of your gear stage. So do that before you go to the microgeometry. Microgeometry is again profile modification and flank line modification. And microgeometry optimization is more time consuming than all the rest, because you may get from tooth contact analysis, and you need to tooth contact analysis for microgeometry evaluation. You may get this type of nice pictures, but here it's very hard to see what do you now change to get a better contact pattern, to get an improved noise level. So what we developed in the last, in the last years for the stage 3, we have 3 steps. We do a first step where we just define the theoretical flank line modifications. For that we have a new tool based on an ISO Annex I to ISO Part 1, ISO 636 Part 1, which is very, very helpful, very fast to get the optimum flank line modifications. Then we have to add something to compensate tolerances for parallelism of shafts in the housing, and tolerances for the flank line in manufacturing of the gears. And at the stage 3, step 3, here then we will optimize the profile modifications. So this is the target. I will now start, and I will call for that a little bit a simpler model. The background is then contact analysis is pretty fast running, otherwise it's too much time consuming. I go back to the spare gear as example number 1 without any modification in the moment, and in the factors I will change something. If I would like to compensate the bending of the gear, the gap between the gears due to bending, I have to join in or to get in the bending of the shafts. So I go now on the phase load factor to the calculation without manufacturing allowance, but according ISO Annex I. And in axis alignment, now I'm on input. I change that. I go on from shaft calculation, and I have to select to get in here to choose the correct, where is that? Gear shaft for cylindrical gear pair 1. So I add I have just to add the saved shaft calculation from the KISSsoft shaft and I say okay. Have a look now. This KH beta was 1.06 based on ISO normal standard. If I do a calculation in behind, the shaft calculations are running, and I get 1.4 Y. Y is here. You see it in evaluation under gap analysis. This is now based on the bending of the two shafts, the bending combined, deformations combined. You under this thing here. I click out in the moment here. So this is now the gap between the two meshings, between the two face widths, from the left side to the right side of the gear. So you see, we go from basically 0 gap up to a gap of 27 micrometers. Doesn't say much to you in the moment, so please change to face load distribution. And now this shows now the line load Newton per millimeter from left to right. You see, where the gap is 0, I have the highest load. That's clear because in between we have the tooth stiffness, and based on tooth stiffness we can calculate from the gap, we calculate the load distribution. Very simple. And what you see here, because of this very bad load distribution, this is horrible, and that's why you get a KH beta of 1.42. So now what I would like to do is I try to figure out what modifications are needed to compensate for the deformation of the shafts. It's quite easy. We have here a sizing modification tool, very nice thing, and we go here. We don't want to size actually the tip, the profile. We want to size the tooth trace. So exact sizing according ISO standard. This calculation method we just choose. That's okay. We want to do that. I just say calculate, and you see the proposition now here is for gear 1 and for gear 2 a small crowning of 1.4 micrometers and a relatively big helix angle modification. For the expert between you, it's clear if you have such a basically linear from left to right side bed distribution, you must compensate that mostly by helix angle modification. I say just accept. The values are now here. I can redo the calculation. Now the calculation is considering the crowning, and with that I can check if the proposition here, which was given by the software, is satisfactory or not. We'll make it a little bit bigger. Okay, I can sorry, close that. And you see now, you don't tell me it's bad. It's much better, but it's misleading that the axis here is now from 480 to 648 to 658. So basically the line load is uniform. So this is a very good solution, and you see it here. The KH beta is 1.005. So basically telling us this is a perfect, nearly perfect solution. Okay. Now this is what is needed to compensate the deformation. But we have also manufacturing tolerances, and manufacturing tolerances will change the gap from left to right side of the meshing of the face width, because and we don't know if there are plus or minus. there are tolerances, so they can, in manufacturing, they can be plus or minus. And what we do now is that we change here under factors, and we tell the software we would like to consider manufacturing allowance. You can use the button here now, and here the software makes proposition. The software tells you the helix slope deviation based on the ISO quality chosen in the basic data tab is 10 pinion 11 for the gear, and then we have a non-parallelism of the shafts in the contact plane of 24. This is based again on an ISO standard for axe parallelism. So we have two propositions. One is the maximum proposition, means just added 10 to 11, and this is absolutely the worst case. Should basically will never happen, because in manufacturing normally you measure and you see you are out of the tolerances, then you have to redo it. So we use here statistically evaluated probability, which would then propose these numbers here. So I click here and I get these values here. Now what we have to do is we calculate the load distribution based on this annex philosophy 5 times. First time without tolerances, as we did before, we will get this value again, and then we do it with plus on the left side FH beta, plus on the left side FMA, minus on the right side all the combinations. So if I redo the calculation now, you will see it takes a little bit more time. This is the load distribution, and this is the gap analysis. So for all the combinations, we have different gaps. So to compensate for that, I go back to the load. This is clearly, this would be nice, but this is very bad. So we have to do something that in the worst case means in these two cases that we don't have edge contact, the highest load on the right or on the left side. So here ISO standard in an annex is giving says you could suggestion, I may say, suggestion to use about the FH beta value. So we just will try that. I will add here, you see, sorry again, it was too fast. I have 15 micro error there. So under modification, I will put an increased crowning just on the gear 1. I just add here to this 1.4, 15. So let's say make it 16 micro crowning. So much higher crowning in order to try to improve here the situation. We just recalculate. Takes a little bit of time, and you see what happens. Now we are much better. We don't have anymore a perfect flank line load distribution. That's not possible because we have now an exaggerated crowning to compensate for the worst case of manufacturing tolerances. But you see the two bad cases from before, they are much nicer now. We have a maximum about 15 to 20% on the inner side of the face width. So this is a little bit, let's say, feeling. There is not a strict rule. My rule is highest load not on the left and not on the right side. Otherwise, we have to make a compromise. And I think it's not a two. The compromise is quite okay. You will see we have now KH beta here in the first case 1.112, 1.22. So we are better than before. So we can say that's okay. Okay. So all these modifications are now just applied to compensate the load distribution over the phase width. All the flank-line modifications have the same aim. We want a best possible load distribution over the phase width. Flank-line modification for noise and so on have little impact. So this is all. Now we have to add the profile modifications. And profile modifications are more time consuming to calculate. We are now calling, I'm sorry, I go back here. Okay. I'm sorry, that was a mistake. I stay here. I will just load more simplified without shafts, because shaft calculation included is also time consuming in calculation. I will just call the simple cylindrical gear set number 1 and open the reference profile. One thing I forgot, I can let it open, doesn't matter. I will open here the modifications and I will reuse the sizing buttons, but now for the tip and root relief. And I will tell the software here, use a long arc-like modification. To reduce noise, long modifications are a must. Short modifications, short profile modifications, never, or in basically no case, are improving the noise. Long, a lot. And arc-like is has a little bit better behavior than linear. If I click here on calculate, you see the proposition. These are a very simple rule behind from the Niemann book to use approx 40 micrometers and length factor of 2. If I say accept, these values are then available here in the modification. If I now go back here in modification sizing, I have a condition 1. Here I will add all the modification which I do not want to vary. But to get noise optimization, I would like to vary the profile modification. So I can just click here. Okay, I have to make the calculation consistent and I retry. So now it's working. And you see here I can tell the software, okay, I would like to have to vary, for example, in 5 steps here, the value from 20 to, let's say, 70. I can say the factor should be constant, that's okay. Same thing for 20 to 50. Plus, I can say under conditions 1, additionally to all these combinations here, additionally to also calculate everything for example 80 and with 2 steps, 80 and 100% of the load. So the idea here is we do all the calculation for 80% of the load and for 100%, because I would like to see if a specific modification, one of these combinations here, is also good for 80% and not only for 100%. I do not run the software now because we are a little bit short in time. I already let it run and I have it here. The same example, you have here all in condition 1, all the flank line modifications I changed before. I do not vary them because they are already okay. I did here another thing again. I used the cross variation, and I told here that I can change it to here, number 1, number 2, gear 1 and gear 2, they are synchronized. What does this mean? That means we calculate many solutions. We do calculate from 10 to 120 and from 0.2 to 0.4 as lengths, and that we cross-correlate with the gear 2. So we do with the first setting 10 and length 0.2, we do all the variations of the gear, of the second gear, and then we increase to the next step will be 20 with all the factors, with all the combination of the gears. So when I would click here on calculate, I get about 300 solutions, and this takes time. So what you see here is then the results. Again, we have a result table as before. I can again click to the numbers. You see here the peak-to-peak transmission error. You see the effective overlap ratio under load, the maximum Hertz pressure, the safety for microbeating, efficiency, and. But the nicest thing is then here you have a similar graphic as you have seen. The idea is similar to what you have seen in the file sizing, but clearly what we display here are other things. For example, here you see the value of gear 1 from 0 to 120 micrometers, and in color the length of the modification. Where did we start the modification? So long modification is about a factor of 2, a short one is about a factor of 1, and you see here at a certain tip relief around 40 to 50 micrometers we have the lowest transmission error. And the longer it is, our modifications, the better it is. Let's say 47, 48 are not very far away, but the short factors are clearly bad for transmission error. You may say, yes, transmission error is nice, but maybe for me also, for example, the power losses in automotive, power losses are very important, and you see here in power losses, now the highest value is the best one, the nearest to 100%. So this is going up, and you see again, let's say the 50 millimeters, which was optimum for noise, is not, let's say, it's not bad for efficiency, but it will become a little bit better higher up. But long modifications are still very good for efficiency. Maybe last thing to show you, we can have the microbeating safety to see how the microbeating safety is behaving. Also here, relatively, fortunately, we see also always a CA, a tip relief of around 50 seems to be very good option for that. In graphic 1, just shortly, you see we have a so-called spider diagram. Here, actually, as I was running this thing now only with 100%, I just see, oh sorry, one blue line. If I would have, if I would do the same thing for 80 or 70 torque, then you would have here another color of line. So here you see how fast things are changing if we have different torque conditions. Okay, I'm through. It was a little bit fast, but we are nearly out of time, so we want to leave some time for questions. we have some documents available for you. Can you handouts? I don't see it.
Yes, we have some documents. You can download them at handouts in the GoToWebinar tool, or afterwards you can download them as well. We put them online. Another thing is I realized some of you might have had audio issues. I got some questions because of that. You get also later, after we uploaded the video, you can get it on YouTube, I think, and can have a look, or you get it by download link. So that's not a problem. Unfortunately, I don't have the questions we could now answer live here in the webinar. So I think I would like then to thank you to Dr. Kissling for all the attendees which are joined now, and I hope you got quite a lot of information for you for your next project. Thank you.
Thank you. Goodbye. Have a good day.